Hello again, folks. So we're going to continue by looking at how we're going to analyze individual compounds. Now, this video is a little bit more math intensive, so bear with me. But this video will discuss about empirical formula, molecular formula, and the way scientists actually strive to achieve finding out such things like what an unknown compound is by analyzing things regarding its weight. There's ways to find out its molar mass easily enough, but once you have the molar mass, unless you have very, very expensive equipment with very, very accurate detectors, it becomes kind of a guessing game of what atoms are needed to add up to give you that molar mass. And we're going to talk about combustion analysis, which is a rather, somewhat simple way to achieve that goal, especially when we're dealing with organic-based compounds. Okay, without further ado, let's look at these slides. So, the idea here is when we're analyzing unknown compounds, we may know we can weigh it out and know the mass of what we're dealing with. We can find its molar mass. We might even be able to know its percent composition. But unless we have some foreknowledge, we rarely know its chemical formula. Unless we know what it is we're working with from the get-go, we won't know its chemical formula. A lot of science, you got to remember, on paper it all seems very simple, but in reality we're looking at a black box of maybe some crystal or some oil that we may have isolated. And unless you already knew what you're starting with and what we're mixing together, you rarely, if ever, know what you have. If you take a really complex molecule, like say a plant, and you're rendering down the plant to get certain ingredients out of the plant, different steps are going to give you different ingredients, and sometimes they're going to be a mixture of ingredients, and then you're going to try to separate those. Each one is going to be very different and sometimes have very different masses and chemical formulas. And so without knowing exactly what we have, how do we go about finding out what we have? So before we go deeply into that, we need to discuss the difference between molecular formula and empirical formula. The molecular formula is essentially, if you have a distinct molecule, it is the actual number of atoms of each element present in a single molecule or given compound. If you say I have a cube that is made up entirely of sucrose, a simple sugar, that's going to be C12H24O11. It's going to be 12 carbons, 24 hydrogens, 11 oxygens. That's exactly it. It's going to be, if I say glucose, a simpler sugar, it's going to be C6H12O6. 6 carbons, 12 hydrogens, 6 oxygens. So, there's essentially every compound is unique. Every compound is, actually there might be sucrose might be H22. It doesn't really matter right now, but the idea here is that it's the total number of each atoms. When you talk about an empirical formula, empirical means something that is readily observable. When we're looking at a molecule on a blackboard, yeah, it's readily observable. But if we're looking at a cube of sugar on a table, you can't not you cannot observe how many of each atoms are there. We can't. All we can do is when we burn it, collect the carbons, collect the hydrogens, collect the oxygens, and from that, readily observe what ratios we get. The empirical formula is essentially looking at the simplest whole number ratios of each element. So sometimes these guys may match, but sometimes they won't. Glucose, as I said, C6H12O6, has one carbon for every two hydrogens and one oxygen for every one carbon. It's a 1 to 2 to 1 ratio. You know what also has a 1 to 2 to 1 ratio? Formaldehyde. Formaldehyde, which is actually C1H2O1. So they have the same empirical formula, but one is already done. The other is a lot more complicated. But if we can readily get the empirical formula of something just by analyzing the percent composition. Because the percent composition, if we know each thing's masses, we can figure out how many of each guy they are based on the weight. Now, there are some compounds, well, actually, some things that cannot have a molecular formula because by their very nature, they are not an individual molecule. You have covalent and ionic solids can only be represented by empirical formula, the things that only get formula units. Sodium chloride is made up of, as I said, billions upon billions of sodiums and chlorines. But the simplest whole number ratio is a 1 to 1. Glass or sand is made up of silicon and oxygen in ratios of 1 to 2. But it goes on and on and on and on. Diamond and graphite is just pure carbon in a repeating pattern. It simplifies just to carbon. And so we cannot represent them any way more complex because they are not individual molecules. But here is the mathematical way we can determine empirical formula of a compound that's made up of element A and element B. So we will always start with the end goal is always to compare a ratio of moles of each element. We can only compare moles. Why moles? Because moles are our counting unit. You could technically go to atoms. Atoms would just add one more step, one unnecessary step. So we're always going to compare moles because each atom weighs a different amount based on its molar mass. So if we compare moles, those are direct ratios. Now we could start from one of three places and still go into moles. It is relatively easy. If we start with moles, oh good, we can directly compare. What is more likely is we'll either start at mass or percent by mass composition. However, mass is relatively easy to deal with because mass can be converted into moles by dividing by molar mass. If I look at the mass of a given element and I divide by that element's molar mass, it gives us the moles. We can do that. If you have a percent by mass, we can directly convert that into a mass without much difficulty. The easiest way to do this is to take that percent and just directly convert that into mass. We will make an assumption of 100, and we can just say mass percent is equal to mass. Full stop. But our goal is to get a ratio of moles of A to moles of B. Once we have that, that ratio will give us the subscripts of our empirical formula. So if our goal is to compare ratio of moles, we want to find the simplest integer ratio. Because one of those Dalton's rules of Dalton's law deals with that they must combine in simple whole number ratios. So if the mole ratio is close to a whole number, we're going to assume maybe there was some degree of uncertainty in the measuring of it. Or maybe we introduced some degree of uncertainty by rounding unnecessarily in the molar mass calculations. So like if I had a ratio of 1 to 1.98 or 1 to 3.02, feel free to round that to 2 or 3 respectively. However, if it is much farther than that, consult this decimal chart and convert this into a fraction. See the decimals 0.2, 0.4, 0.6, 0.8 is a ratio of 1 to 5, 2 to 5, 3 to 5, 4 to 5. Less likely to get those. You're more likely to get a 1 to 3 or 2 to 3 ratio. You might get a 3 to 4 or 1 to 2 or 1 to 4 ratio. So look at those ratios. If you get anywhere close to those numbers, consult the chart and see what would make the most sense. What would make the most sense? So, for the example I have right here, if I have a sample that contains 19 grams of nitrogen and 4.4 grams of oxygen, what is the ratio of nitrogen to oxygen? So step 1 is convert 19 grams of nitrogen to moles. So I'm going to divide that by the molar mass of 14. You do that, you get 1.36 moles. Do the same with oxygen, 54.4% grams of oxygen. Divide that by 16, you get 3.4. Now the ratio is 1.36 to 3.4, which if you simplify that is 1 to 2.54. I'm going to say that is 1 to 2.5. So there's nothing really big. 0.54 is closer to 0.5 than it is to 0.67. And so we're going to say it's a 1 to 2.5 ratio. Now we're not allowed to have fractions. So 1 to 2.5 is the same as a 2 to 5 ratio. So my empirical formula is N2O5. 5 oxygens for every 2 nitrogens. And that is a reasonable number. If I tried to make a smaller fraction, it's going to get very nitpicky. So these fractions are usually more than convenient enough. So let's look at this. Before we go on any harder, copper and oxygen. So copper, oxygen 0.853 moles, and oxygen of 0.4265 moles. And then I got an iron and chlorine, 31.83 grams of iron, and 60.62 grams of chlorine. So let's look at these guys, if you don't mind. Okay. So the first thing is, since they're both in moles, we're going to set a ratio of the smallest one on bottom, the biggest one on top. We just need to divide those and see what does that give us. 5.3 divided by 0.5 0.4265. That gives us a ratio, that answer of 2, which means this is a ratio of 2 over 1. So with that in mind, our empirical formula is Cu2O. That one is particularly easy. And that means that's copper 1 oxide. What about this? Iron chloride. Is it iron 2 chloride or iron 3 chloride? Which is it? Well, for this, we need our molar masses. We cannot just compare these guys, because if you just compared it right there, right here, you would say it's about a 1-to-2 ratio. That iron weighs, iron is about half as much. But the molar mass of iron is, as we said, 55.85, and the molar mass of chlorine is, we'll say, 35.45. Where did I pull that out? I pulled that out of my handy little textbook. Where will you pull it out? You'll pull it out of your handy little textbook. Or you'll pull it out from online. Or you'll pull it out from the useful information sheet. Wherever you have a periodic table, that's where you're going to do it. So, okay. We got to work this out. So, with 31.83 grams of iron, we need to convert this into moles of iron. 5.85 grams, 1 mole. Now, chlorine, 60.62 grams. Same math. The only difference is molar mass. Different molar mass. But the same steps. Grams cancels grams. Grams cancels grams. Let's see. What is 31.83 divided by 55.85? You do that. 56.99. 0.5699 and 60.62 divided by 35.45 gives you 1.71. But so that's moles per moles. So we're going to put the big number on top and divide by the small number. 99. So 1.7100 divided by 0.5699 gives us something like 30005. So that's essentially 3 to 1. This is chlorine. This is iron, so our empirical formula is FeCl3. 3 chlorines for every 1 iron. And that's what it must be. And we found that just by comparing the mole ratios. Mole ratios. One more. This one's a little bit trickier. 100 grams of a compound contains 23.5. That's it. Yeah, 23.5 grams of 23.5% oxygen, 70.6% carbon, and 5.9% hydrogen. And so we have to then go, okay, that all well and good. Well, how do we do this? Well, there's 100 grams. Well, as 100 grams, 23.5 goes mass of oxygen over 100 times 100. What does that mean? 100 over 100, these guys are going to cancel out. So what does that mean for us? We have 23.5 grams of oxygen, 70.6 grams of carbon, 5.9 grams of hydrogen. Even if we didn't have 100 grams, we can assume 100 grams. If they gave us 300 grams, each of these numbers would be 3 times greater. So it doesn't really hurt us or help us if they're 3 times greater or 3 times smaller. It'll work either way. So with that in mind, the molar mass of oxygen is 16 grams per 1 mole. The molar mass of carbon, 12 grams, 1 mole. And the molar mass of hydrogen, because it's essentially not gonna round this, so 1.008 grams of hydrogen per 1 mole. So each of these guys will cancel out. So 23.5 divided by 16 is 1.4, we'll say 69. 70.6 divided by 12 is something like 5.883. And 5.9 divided by 1,008 is 5.853. So that means this is the smallest number. I'm going to divide both these numbers by 1.469. So 5.853 divided by 1.469 is something like 3.98. 0.883 divided by 0.469 is something like 4.00. So what we have here is an empirical formula that is C4H4O1. C4H4O1. 3.98, close enough to 4. That is more or less 4. So that is how you would go about doing that. That is a little bit more labor intensive, but it's absolutely doable. Absolutely doable. Well, now that we have the magical empirical formula, what can we do with that? We can turn that into the molecular formula. We can look at the actual number of each element in the molecule. Sometimes they will be the same. Sometimes it will be the same, and then we have no work to do. But if they're different, first we still need to find the empirical formula. The molar mass is related to the empirical formula by a ratio of formula units. If we look at the empirical formula is a small fraction, some fraction of the molecular formula. Our goal is to find what is that fractional ratio. Is it a 1-to-1, in which case they're the same, or is it a 2-to-1, 3-to-1, 4-to-1? And we're going to increase it by that multiplication factor to get the real formula. So, for example, oxalic acid has a molar mass of 90 grams per mole, but it has an empirical formula of HCO2. 1 hydrogen, 1 carbon, 2 oxygens. So what is its actual molecular formula? Well, that formula unit, that little fragment, is 12, which is the carbon, 1, which is the hydrogen, and 32, which is the oxygens. That fragment weighs 45 grams per mole. With that in mind, 45 goes into 90 2 times, meaning it's a ratio of 2 formula units fit into 1 molecule. So the singular molecule is actually H2C2O4. We've doubled the amount of all the atoms involved. Well, the last little aspect of this, where it can be the most annoying, is how do we actively find these mass percents? That's by a little trick called combustion analysis. While we will rarely use this in class, it's good to know and understand how this is actually done. It's a technique that can determine the empirical formula of just about any hydrocarbon that is largely made up of just carbon and hydrogen. That instead of finding the direct amount of carbon and hydrogen present, it burns the sample in oxygen to form carbon dioxide, which it traps, and hydrogen dioxide, which is our, not hydrogen dioxide, but that forms water, dihydrogen monoxide, which it then traps. And by figuring out how much water and how much CO2 it has trapped, we can figure out essentially what all of how much carbons and hydrogens were present, because it knows how much mass you put into there. So that mass percent in there, the carbons present in the initial sample are responsible for every CO2 produced. The hydrogens in the original sample is responsible for every hydrogen produced. The only problem is that, for example, if there's oxygen present, because it is adding oxygen to make sure it burns, you cannot always figure out exactly how much oxygen is in it directly. However, you can find it indirectly, because if you figure out the mass percent of carbon and the mass percent of hydrogen, well, any remaining mass percent that is missing must come from something else, like oxygen. Like if you find in a 100-gram sample, like 50 grams are coming from carbon and then 25 grams are coming from hydrogen, well, we've used up 75% of the mass. So that means the other 25% must be coming from something like oxygen. So just keep in mind, since it's a percent, everything must add up to 100. Now, a problem like this will typically have 4 pieces of information. They will have an initial mass of our sample. We will be given something like the total molar mass. We need to find out what the molar mass is so that we can find the empirical formula. Then the problem will give you the mass of carbon dioxide captured and the mass of water captured. So these 4 pieces are all you need to know to find out your molecular formula. Now, if there's only carbon and hydrogen present, well, here's what you do. You use the mass of CO2, and that can be directly converted into moles of CO2. And for every 1 mole of CO2, you have 1 mole of carbon. The mass of water Well, we can convert that into moles of water. And for every 1 mole of water, you get 2 moles of hydrogen, because there's 2 hydrogens in 1 water. And from there, the moles to moles gives us the empirical formula. Once we have the empirical formula, we use the molar mass to find the molecular formula. However, if there's another element, such as nitrogen or oxygen, another step must be considered. Since oxygen is added during the combustion, the captured gas doesn't. Yeah, I just said that. However, once again, if we note the carbon or hydrogen present as the percent composition, everything left of the initial mass must come from the missing element. So, for example, if we find out that a 100-gram sample you would have to find the moles of carbon produced and the moles of hydrogen produced. We could convert them into the relative mass of carbon and hydrogen. That relative mass can be subtracted from our initial 100-gram sample. Whatever mass didn't come from carbon and hydrogen came from oxygen. And from there, we can figure out how many moles of oxygen did we have. So, take, for example, this problem. A particular sample of hydrocarbon jet fuel weighs 100 grams. This produced 323 grams of CO2 and 106 grams of water. If the molar mass for this compound was 136.2, what is the molecular formula? So, we turn the 323 grams of CO2 to moles, and then from moles of CO2 to moles of carbon. So that gives us 7.34 moles of C. Then we take 106 grams, divide by 18, multiply by 2, because each water has 2 hydrogens. Gives us 11.8. We find the simple ratio, and it's a 1.6 to 1, or 1 3/5 to 1. To make this a whole number, we have to multiply by 5. And so we get an 8 to 5 ratio. So C5H8. Now, how much does C5H8 weigh? We add up 5 carbons at 12, 8 hydrogens at 1, weighs about 68. 68 goes into 136 about 2 times. So our empirical formula is double C5H8, which is C10H16. So with that in mind, that is some sort of a hydrocarbon with 2 degrees of unsaturation. So some sort of decane or cyclodecane with 2 degrees of unsaturation. Now, looking at this, one more complicated problem before we try one of our own. A 50-gram sample of a simple sugar containing carbon, hydrogen, oxygen produced 72.1 grams of CO2 and 36.8 grams of water. The molar mass is 122.12. What is the molecular formula? Same process, we're turning grams of CO2 to moles of carbon, and grams of H2O to moles of hydrogen. However, in addition to that, we are converting them back into carbon and hydrogen so that we know how much oxygen is present. So with that in mind, 1.64 times 12 is 19.7. 409 times 1 is about 4.12. So if I subtract the carbon and the hydrogen from our 50 grams, we'd say there's 26.2 grams of oxygen. If we divide that by the molar mass of oxygen, 16, we get 1.64. So what is the simple whole number ratio between these guys? Well, carbon 1.64 and 1.64 is a 1-to-1. 409 and 1.64 is about 2.5 to 1, which is 5 to 2. So if it's a 5 to 2, it has to be a 2 to 2 to 5 ratio, or C2H5O2. Now, how much does this fraction weigh? This fraction weighs 61. How many times does 61 go into 122? That goes into it twice. So our simple sugar is C4H10O4. C4H10O4. Simple enough. This is the last slide. We will finish with this problem. It is still labor intensive, though it's not too bad. 20.0 grams of hydrocarbons C and H. We have a molar mass of 78.114 grams per mole, and we have 67.6 grams CO2, 13.8 grams of H2O. So let's look at this. We'll finish this off. Okay, with that in mind. Step 1. Convert the grams of CO2 to moles of CO2. Carbon is 12. Oxygen is 16. There's 2 of them. That is 44. 44 grams of CO2 and 1 mole of CO2. 1 mole of CO2 produces 1 mole of C. Note, each step cancels the last step. I always strive for that. 67.6 divided by 44 times 1 is 1.54. I won't say 54. It's 536, but 54 is good enough. That's moles of carbon. So 13.8 grams of water. Hydrogen is 1. You double it. And oxygen, it's 18. 18 grams of water. 1 mole of water. But remember, because of this 2, for every 1 mole of water, it produces 2 moles of H. So 13.8 divided by 18 times 2. 1.53. That's close enough to 1.54. So we have a simply 1 C1 H1 ratio. How much does that weigh? Well, 12 plus 1 is about 13. And 78 divided by 13 is what? 13 is 6. So our empirical formula may be C1H1, but our molecular formula is C6H6. C6H6, because 13 goes into 78 6 times. That's where we'll stop. And that is, while we probably won't see these type of problems very often, being familiar with them helps you understand some of the math people must actually consider in the real world when they're going about discovery. It's not just like a walk in the park. It is actually, there's a systematic way we have to go about these things. Anyway, have a good day.